Announcements. Before I introduce today's speaker, I just want to make an announcement. There is the next meeting, our next event for the graduates in nanotechnology, which is the student group for the IEN, nanotechnology and other IRIs. We'll be meeting a week from today at 11 o'clock on January 29th. That is a week from today. And it'll be an event meeting with Rebecca Horton, who is the representative from Sandia National Labs here at Georgia Tech and part of the Academic Alliance program with Sandia. So that will be at 11 o'clock. They'll be meeting in the small first floor conference room in this building in Marcus. It's room 1113. And if you are interested in attending, you should send an email to Leslie O'Neill, who is part of the education program here at IEN. So before today's speaker, we'll be meeting next on February 12th, and the speaker will be Shu Jia from BME. So it's a real pleasure to have today's speaker, Natalie Stingelin, who's a professor in material science and engineering. Natalie got both her undergraduate and doctoral degrees at the ETH Zurich in material science and engineering. She was then a postdoc at the Cavendish Lab at Cambridge, and then had a number of research and teaching positions in the Netherlands, at the Queen Mary University of London and Imperial College, before coming to Georgia Tech in 2016, where she's currently a professor in MSc as well as chemical and biomolecular engineering. She's a fellow of the Royal Society of Chemistry, among other honors, and is associate editor for the Journal of Material Chemistry. So it's a real pleasure to have her with us today.
Okay, thank you very much for the invitation. I only moved 2 years ago, so I'm only exploring now all the different institutes here at Georgia Tech, especially also the Institute of Electronics and Nanotechnology, which is pretty much at heart of my research. When I was at Philips, for instance, I was working in the transistor unit. Today, I present a bit of a new topic. I'm really a trained polymer scientist. But more and more I went off into electronics, but now I got intrigued about light. And coming from the polymer world, nowadays when you explain to people that you work on plastics, you often get in trouble. They say, really, you know, they pollute, etc. So you always have to find a story to say that actually your research, hopefully actually, will have impact. So what we really have to try, I think, as a polymer scientists and possibly as material scientists in general, is to show that new smart plastics actually can do good things for the environment. So it's not only the straws and plastic bottles that end up in the sea, and to be fair, it's not the bottles' fault that they end up in the sea, it's the people who don't recycle, but obviously that's not what people want to hear. Anyway, unfortunately, we get always this picture and people relate to it, and so we as scientists have duty, I think, to change that picture, hopefully get the news, better news on plastics, because there are a lot of opportunities. In one of the fields, like bioelectronics, conducting polymers more and more get into the health business for electrical recording and stimulation, cell culture and tissue engineering, or chemical release and delivery. More and more up and coming are neuromorphic computing. So this is actually really mimicking the neurons in our body, but making actually not artificial neurons, but hook up, use them as guidance, how we can get to new computer systems that actually learn how to operate. And interestingly, polymers work in many cases better than inorganic materials. They're also more versatile. A field I worked in for a long time, organic solar cells, while obviously the organic or plastic solar cells are still lower in efficiencies, more and more we get there. Recent reports say we get to 17%, and the ease, and I will show that, of having plastics in the solar cells, it's not necessarily the efficiency, but they're semi-transparent. We can put them into buildings, integrate in the windows, etc. So plastics can have good benefits. Though as mentioned, more and more, I was interested to not only guide or use plastics for electronic purposes, but what about light? I mean, we know a lot of fiber optics. We use PMMA derivatives, plastic glass especially. But can we get further and really use plastic photonics and maybe in future plastic integrated photonic systems? Why would light be so interesting? With light, we can do whatever we do actually with electronics. We can transmit signals, we can amplify signals, we can detect signals, we can modulate systems or signals, and we can integrate, as mentioned, photonics integrated circuits. But light, contrary to electrons, photons, they move faster. And everybody who works on electronics, definitely in the organic world in particular, we always fight about traps, holes, the positive charges or electrons, the negative charges, recombining, which can be good in solar cells, but most of the time it happens at the wrong time or location. With light, we don't have this issue. And therefore, they would be very interesting for applications such as mirrors. Sounds simplistic, but we can do a lot with mirrors. Just go into a femtosecond lab and you see how useful they can be. Lenses, clearly we maybe don't talk about cameras here, but when you think about lenses for space applications, solar cells, as I mentioned, laser, and what I also will focus a bit on is heat management. Possibly not really an issue where I come from in Switzerland, but here in Atlanta in summertime, definitely a big issue. With all these promises, though, you think, why are photonic devices and objects not so much more used? Well, so far, and I have to apologize to the inorganic materials people, processing is still very, very intricate. You can actually make beautiful inorganic photonic devices, but processing routes are very intricate, often low versatility, though you can make beautiful structures, and most importantly, when you think of building integration, limited size. And they're rigid. Similar like with solar cells, rigidity and weight plays a significant role. So using plastics could actually open up new options and markets. So what can we do? Why people haven't used organics yet, except for light fibers, is organics have one big issue. They're in particular made up of carbon and hydrogen, if you're lucky some nitrogen, and if you go to the conducting material, sulfur or so. But therefore, the refractive index is really small. And it's not necessarily the value that counts when you do photonic devices, but it's the contrast. But you see, you're very limited in getting large refractive index contrast with organics. That's why people use inorganics, and to be fair to the inorganics, they really cover the whole range. So it's very easy, in principle, to make photonic devices because you can reach very high refractive index contrasts. One solution, and obviously we're not the first one, is to combine the two worlds. Let's have inorganics mixed together with organics. So here you get the processability, large-scale potential, but with the inorganic optical properties. And there's two options. You can use nanocomposites or hybrid materials. Nanocomposites is possibly the most investigated pathway, but this picture immediately shows why nanocomposites, in case you want to do high-quality photonics, have a problem. First of all, here they used actually lead sulfide. Why did lead sulfide nanoparticles? So these dark particles are lead sulfide. Why lead sulfide? High refractive index. But lead sulfide, of course, also absorbs. So you immediately have issues in case you want to make the, photonic devices for the visible wavelength regime. More importantly, even when you use something that doesn't absorb in the visible or infrared, depending on the region you want to manipulate light, particles have a strong tendency to aggregate. And once they aggregate, they will scatter light. And once you scatter light, you have losses in case you want to make waveguides, you want to make mirrors that reflect, etc. So we decided not to go via the nanocomposite pathway. Clearly, you can reach higher refractive index. So you see here nicely, because of the high refractive index of the, and I use now my nice tool, the lead sulfide, you see when you add more lead sulfide in, you get to decent refractive index for organic-based material here, the organic meaning the polyurethane PTU. However, the scattering now comes when you measure transmission. So here we just have the polyurethane by itself, very good. But as soon as you already add little of the lead sulfide particles, you see this tail coming up, which is simply scattering. So that means you can't use your material pretty up to like 650 nanometer. And the more you add, actually, you get unwanted absorption because of the particles. We want to have materials that are as open, as transmittive in a system, in the visible as possible. An elegant pathway was this, what I think is more a hybrid. The authors actually drew here particles. In reality, I believe there's more like an inorganic polymer made up of titanium, oxygen, and titanium. And when they actually measured the refractive index, they saw also pretty much an increase of refractive index. And in this case, they actually got what is pretty desirable. So the polymer is essentially unaffected by the particles, and what I would call the hybrid and the neat polymer have very similar transmittance. However, A, I'm not a chemist, but B, even as a polymer scientist, this backbone looks awful to process. Very likely, very low solubility because you don't have really solubilizing side chains. You have a pretty rigid backbone. So you will have limited molecular weight. So mechanical properties will be low, etc. So you get the optical properties, but for all the rest, you would not really call it a plastic. So this showed us, and that was now possibly 10 years ago, still at Imperial College, there's really a need for plastic materials that are A, easy to synthesize, processable, solution would be nice, of course. We need, though, to tune the refractive index. However, we need to do so without changing the transmission, so the optical loss should be 0 or as close to 0. And for future applications, we should be able to pattern the material, so actually we can really do photonic crystals. So what did we do? Well, not being chemists, we simply thought, okay, why don't we just use a bulk commodity polymer, polyvinyl alcohol, often used, actually all Coke bottles have a polyvinyl alcohol coating, it's a derivative on it because it's a very good oxygen scavenger. So this we can buy in any molecular weight, so any chain length, and we just added, very similar to the paper I showed, a titanium dioxide precursor. Why? Usually this titanium dioxide precursor would interact with itself and actually produce titanium dioxide. But now, in case you have the polyvinyl alcohol around it, these alcohol groups here will interact and actually conduct a hydrolysis with the precursor. So very similar, like in the previous paper I showed, we should actually expect to get essentially a very messy hybrid made up of polyvinyl alcohol chains and titanium oxygen titanium chains with still some end groups from the precursor. Why is that so important? We try not to form particles, but we try to actually make epoxy where we cross-link the polyvinyl alcohol with the titanium oxide, titanium polymer, or vice versa, depending on the amount you have. And you see it works beautifully already when you make a picture of a film of the hybrid. It's very difficult to see. It's beautiful and transparent. Very different to, for instance, composites where we just add nanoparticles into the film, where you immediately see the scattering effect. Even while titanium dioxide doesn't absorb, because of the aggregation of the nanoparticles, you get this unwanted loss because of scattering. And we can do that with thicker layers. So here we produce the lens. Clearly, mechanical properties still a problem, but that can be solved with higher molecular weight. And refractive index is obviously good. I hope you see it here. Here you see the coated area of just the usual cellophane film. And where we coated it, the material looks shiny simply because you increase the refractive index. So it looks actually metallic. And I have to say, and no offense to the physicists in the audience, everybody can synthesize it. So I had chemical engineering students, material science students, physics students. It's amazingly reproducible, actually something I still don't understand, because it's really just mixing two compounds in a pot. We obviously can solution process based, depending on the precursor we use, water or alcohols. And I will now show we can easily tune the refractive index, as we already see here. Optical loss is low, as this picture already indicates. And in case I have time, I will show that we can actually also pattern this material towards photonic structures. The first refractive index. So we did ellipsometry, and you see already, not surprising, the higher the material's content, going from neat polymer alcohol, 20%, 40, and 80 volume percent of titania. We increase the refractive index. What is pretty unusual is we have a low dispersion. So it means that the refractive index doesn't really change with wavelength. This indicates already that we only start to have absorption over here. So it sort of supports already the idea that we have a very low absorbing material. Only at the very high content we have somewhat a dispersion, and the reason is really the titanium species absorption at 300 comes in. As a material scientist, though, what is nice to see is a very nice linear dependency of refractive index with content. What does that mean? And it doesn't matter if we deduce it at 400, 800. This really shows us that the titanium species is very homogeneously distributed in our hybrid material. Otherwise, in case we would start have aggregation or something, it would actually start to level off here. So this is an indirect proof of the quality of the dispersion of the titania. And as a tool, what is nice, oops, that was too much. It's not only that we can manipulate the refractive index with composition, but also with heating. And that's easily explained because we promote the condensation further, we densify the material, and especially for the high content material, we reach decent refractive index of 2.1. And again, it's not the highest refractive index that really matters, but in case you now have a material close to 2.1 and you use it with the lowest refractive index material, polymer at least, that exists, which is 1.29, you get a very, very good refractive index contrast. So just to summarize, so we have a simple material that with titanium content and annealing temperature, we can change refractive index from 1.55 for the neat material to around 2.1 when we go to very high titanium content. We can look though also at the loss. As I said, higher refractive index composites, hybrids have been shown. But what is really critical in case you want to do photonics is that you do not have optical loss, meaning absorption, scattering, etc. How do you measure this? A very simple method are just using Fabry-Perot oscillations that you can deduce from simple UV-Vis measurements. So in case you have a film in an environment with a different refractive index, you will have interference, constructive and deconstructive ones, and they will give rise in your transmission spectra to these type of oscillations. So these are really the Fabry-Perot oscillations. And we can easily learn things from them. From the height, we learn about the refractive index contrast. So the higher the contrast, the larger is the intensity of these oscillations. From the width, we learn about the thickness of the film. And this is shown here, just calculations. In case you have a refractive index of 1.6, you see the oscillations, the maxima actually hit the transmission of the substrate or the neat material. In case you increase the refractive index from 1.6 and 2, you see the oscillations get more deep. Where the loss comes in is, and that's what people often forget, you still have oscillations when you have a lossy material, for instance, one that absorbs, but these oscillations do not hit anymore the transmission of the substrate. So like that, you immediately get a qualitative picture if you have a lossy material. So in our case, we looked at our polymer alcohol here in gray, the glass substrate in black, and two hybrids, 20 and 80%. So you immediately see we have titanium in our films because the absorption of the titanium species comes here. But more importantly, you see these oscillations increase when we increase the titanium content. Also, that's actually what we really wanted to see. The maxima of the oscillations do hit our substrate transmission line. So it tells us we really have negligible absorption. And that even happens after annealing. As I mentioned, when we anneal, we increase refractive index, oscillations get deeper, but we still have the same intensity maxima. And that's actually a bit surprising because people always worried, well, you use polymer alcohol. Everybody knows when you heat the plastics, they're not really the most temperature stable materials around. However, because we actually consume the alcohols with the reaction to titania, one of the most prominent degradation mechanisms for PVA is actually hindered. And we can do that for thick films. Clearly, you can argue what is thick. In our field, 1 micron is actually pretty thick. And then you see beautiful oscillations, and we hit the transmission maxima. Why is that so important? More for the students. When you look at papers, it's very easy, of course, to make anything transparent when you make them thin enough. So this is really the proof that you have a material that does have low optical loss. And finally, you can double check that just comparing the transmission and the reflection. So here on top, you have the transmission. And wherever you have here a minima in your oscillations, you see that's where the reflection is highest. There are really mirror images, again confirming wherever we don't have transmission, we have reflection as expected. So the material is pretty good. Why is that? It took us actually ages. Whenever we try to publish, people ask, yeah, what is the size of the particles, etc. We really had trouble to find particles because it's a hybrid. We don't have particles. So finally, with Gitti Frey and Technion, we could do high-resolution TMM. And you see here the scale bar. It's 5 nanometers. You really have a pretty random distribution. Anything amorphous that you would stick into the TM would look like that. Here, maybe you start to see some brighter areas, but it could just be also the picture. Only when we go to the very, very high content material, 90 volume %, you really see particles occurring. But look here at the scale bar, 20 nanometers. So the particles at the very high content material are still around 1.5 nanometers. So these will not affect optical properties till down to very low wavelengths. That explains the high transparency of the material. Okay, now we finally have a plastic that we can use, hopefully, to guide light. So what shall we do? We went and started to make the most trivial, I think, photonic device, a simple dielectric mirror, a Bragg reflector. So here you just have a multi-layer structure of a high refractive index material, our hybrid, and a low index material. Clearly for polymers, the choice for the low index is actually pretty large. The high index, we used a medium range content hybrid. And then we just stack them, and just for consistency, sometimes I show mirrors when we talk about 5 periods. So it's just a hybrid PFP and then 5 times. Sometimes we add in an extra layer for additional optical effects. So in case, then we call about a 1.5 period. Initially, we worked with this fluoropolymer that is commercially available. Again, why? It has the lowest refractive index, 1.29, and is pretty transparent. And then when we got from 1 period to 2 periods, 3 periods, etc., you see, despite we have 2 transparent materials, as you expect, we start to have a mirror that reflects specific wavelengths depending on the refractive index contrast and the film thickness. Very similar as you find in many of nature's animals like this Ulysses butterfly. We can, of course, quantify this behavior. Here we use the simple PMMA plexiglass as low refractive index material. It has a refractive index of around 1.5, so we reduce a bit the refractive index contrast. But what you see nicely is when you increase the amount of layers, so the glass here in gray, and then you add more and more 1/2 periods, so here 3.5 periods, etc. You nicely see what we call the stop band coming up, the stop band where light is reflected. It is relatively narrow. The reason is the refractive index contrast between PMMA and the hybrid. Since we have polymers, we can easily solution process it. And what was also surprising to us, it's very, very accurate. We can very much define where the Bragg wavelength is. That's the center of the stop band. How do we decide that? With the thicknesses of those layers. Indeed, the Bragg wavelength essentially depends on the refractive index of the layer and the thickness. So one way to change the Bragg wavelength is really just changing D down here. So then you go to thicker layers, you change N star D, and that means you shift it to a higher wavelength. We did that here, so we started first with a mirror with 525 nanometers Bragg wavelength, and once we increased the layer, 700 nanometers. And I have to say, these are really measurements on mirrors that we made, so it's not calculations. So we can tune the color that is reflected of our photonic crystals. And that's shown here, pictures of mirrors that reflect the blue, the green, and here more the orange, yellow. For many applications, it's not only what wavelength is reflected, but how broad. So I will show you examples, for instance, in the heat management, where we want to reflect over a pretty broad wavelength regime. This can be done by really increasing the refractive index contrast a lot. That has also the advantage, the larger the refractive index contrast, the less periods you need to really reflect all the light in that regime. In case you use a very small refractive index, here just simple polystyrene, again plexiglass, where you get a very narrow band, stop band. Important, for instance, in car applications where they want to look at the driver with near infrared, but they don't want to interfere with any other of the light that the driver sees. But you see the issue is the narrower your stop band you want to get, the more layers, the more periods you need. So there's a compromise, and you really have to decide what is best for your application. And in our case, we can tune this, and not only changing from PMMA or polystyrene, but of course, what is nice without changing really the processing, we just can change the content of the hybrid, and like that, change the refractive index contrast. So here we have a high inorganic content material. We needed 7.5 periods to get to a reflection of like 10, bit less %, relatively broad stop band. Once we use a lower content hybrid, so a lower refractive index contrast with the PMMA, the stop band gets more narrow. What we use a lot is the post-annealing. As I showed, with increasing the temperature, we can change the refractive index of the material. And this is simply has to do with the densification of the material. So in the same volume, you have more titanium. This is very reproducible, so we can make master curves how a stop band of a made mirror shifts. So we can make a mirror, and depending on application, we anneal it at different temperatures. We get different refractive indices and thicknesses. So the optical thickness, refractive index times thickness changes. We know why. And therefore, we can change the mirror. So this is highly reproducible. We were a bit surprised because we have sometimes 40 layers in there, which we anneal, but obviously the layers are actually not that thick. So like that, we can, for instance, optimize a mirror that doesn't have a full reflection. When we anneal, we can get to 100% reflection. Clearly, we must know that the mirror does shift after the annealing. And the key is the materials work so well because we have very, very good interfaces. And I think here they're actually equivalent to what you get with inorganic materials. So for instance, when you look at the multilayers with TM, again with Kitty Frey, you see extremely sharp interfaces between the hybrid and PMMA, contrary to like sputtered mirrors, for instance. And we can trace the elements from the titania where it goes to, and we really see no interdiffusion of the titanium species into the lower refractive index material. So this is shown here in case you trace just the titania. You see here in the dark layers where we have the low refractive index. We don't see evidence of the titania. Clearly here we have a lot of carbon coming from the polynyl alcohol. So why important? I promised polymers that hopefully help us a bit with the reputation of plastics. One key structure is light management. So an obvious one coming from a solar cell area is to put them onto solar cells. Why? There's a few options. So in case you have a plastic solar cell, they're actually pretty simple structures. So you have a donor-acceptor mix. That's the active layer that absorbs light and should create the electricity, which is sandwiched between two electrodes, here a transparent oxide, and on the other side, a silver electrode. So organic solar cells, very promising. As mentioned, we get now to 17%. However, they have an issue. We need to keep these active layers pretty thin to ensure that when we create charges here in this active layer, that they get to the electrode. This is a problem because while the organics absorb actually pretty much of the light, you never absorb all the sun that you put in, and you lose a lot because it's not absorbed by the active layer. So what can we do? We can put here a mirror on top that reflects the light that was not absorbed. And that has actually two benefits. So here is a picture of this solar cell and this solar cell mixture. Looks gray. I don't know. It could be potentially interesting for building integration, but what we do when we put the mirror, it's not only enhancing performance, but we change the color. So for architects, they like that actually a lot. So currently, let's say in the perovskite world, they just put a dye on there, so not every single solar cell looks gray. Here, we not only have a dye on there that is inactive, we have a mirror, but it makes the appearance of the solar cell, well, at least make it different. You can argue if more attractive. I guess I like colors. But as mentioned, you can adjust also the light that is shot back. So here in color, you see 3 different mirrors that we put on the back of the solar cell. So the red, green, and blue curve are the transmission spectra of the mirrors. So you see they reflect specific wavelengths. So we can tune it, for instance, that it really reflects in the regime where this material absorbs. So meaning what the light that is not fully absorbed because the layer is too thin goes in here will be shot back. And we see an increase in performance. This maybe doesn't look great, but we can measure it in the JSC. So when we add the mirror, we do increase the JSC because we create more current, because we could absorb more light. And this is shown here. So when we have the usual device, and then devices that really reflect, especially in the regime where the material absorbs, we increase the short circuit current, and that leads actually to a significant increase in the efficiency. So that means even now, solar cells, nowadays we can get 13%. Most of the time, the 17 is really a tandem device. But we can increase the efficiencies, so it makes it more and more attractive to go into these type of applications. More importantly, which would work for all the solar cells, inorganic or organic, we can start to push this reflection band into the near infrared. Why? Especially inorganic solar cells suffer actually when they heat up. So therefore, solar cell, paradoxically, when sun shines on there, they heat up, their efficiency goes down. So we prepared now mirrors that are transparent in the visible, but they reflect the heat, so the near-infrared regime. So here is one spectrum. Nowadays we do much better. It's just actually increasing the layers. But you see here very nicely that our mirror is very open in the visible, and it reflects in the near-infrared. The visible is very open, so we can absorb the light, or the solar cell actually can absorb the light. And here's a picture. I have one in my office. Trust me, there is a multi-layer film in there, so it's really fully transparent. So we aim now to work with NREL to incorporate them not only in the organic solar cell, where actually it's relatively easy because we process them all from solution, but really try to also integrate them in inorganics. And it looks promising because when you look at the inorganic, so that's a silicon cell, they have actually layers, here the eval, that actually helps with light management. So it does give a refractive index matching with the glass, so less light is reflected when it comes in from the glass into the silicon. So here now we can add the heat mirror, preventing the cell actually to heat up, and therefore it will not be affected by the heat. Clearly we can also use the reflected infrared. So this is work by Zach Coleman. So he uses commercially available infrared mirror foils from M, but I have to say they have an advantage that they are made with polystyrene PMMA derivative, so they have a very, very small reflection band in the near infrared. In case you want to really have heat mirror management, you want to have very broad reflection band. And I see my time is possibly starting to end up. So how can we get to broader reflection bands? I showed you we can increase refractive index contrast. With our materials, eventually we get into an issue because I'm not sure how far further we can push our hybrids than 2.1. But an option is just to use chirped mirrors, meaning we use mirrors where with increasing layers, the layers have thicker layer thicknesses. So we introduced by default a mistake in our mirror fabrication. And when we do that, we massively increase the reflection band. So here is actually a mirror that was indeed produced with these 51 or 2 layers. And you see we can get reflection in this case over the whole visible. And actually the film really visibly, the photograph doesn't do it merit, looks like silver, despite it's only made of plastic. And you see that also in transmission. The more layers we have, we go from something green, yellow, to really black, something that was made with fully transparent materials. And in reflection, it gets from the blue that I showed at the beginning to the silvery that really doesn't come up here in this case. So let me use now the last few minutes to get even beyond solar cells. Here I stole a slide from Lin Lu in Princeton, where really heat mirrors will be of interest is smart windows. And that's something I hope we can also sell the public about using plastic for something useful. Because we lose a lot of electricity because of commercial buildings and homes for heating and energy consumption. Actually, here in Atlanta, possibly it's the AC rather than the heating. So the smart window market is really massive. So how can we actually use our mirrors? So what we have to know here, it's not only that we have to manage the near infrared, but especially in colder countries where you want to keep heat in, you also have to manipulate the black body irradiation. So what we thought is we can use commercially available low E glass. So they have actually just an oxide, a transparent oxide layer here that reflects here in the further infrared. And on one side, a DBR of ours that reflects in the near infrared. So here you would have our mid-infrared low E mirror glass that you can buy. And in case we have a usual DBR, we would reflect this, clearly still leaving this part open. However, now when we use the chirped mirror, so the one with the broadband reflection, we actually can nearly cover the whole thing because the chirped mirror in an infrared, near-infrared regime would cover parts of the lower infrared regime versus the low E-glass and the higher reflective index. And these are just calculations of a mirror, a chirped mirror, and superimposed the transmission reflectance spectra of the FTO combined, depending where you shine light in via the mirror or the low E glass, you will get a bit different behavior in reflectance, especially in the near infrared. And once when we make that, so these are now real mirrors in blue, you see we actually get still a pretty high transmittance in the visible. We lose some, and this is actually due because of the oxide layer. And we get a high transmittance here in the mid-infrared regime. Afterwards, the E-glass will take care of it. In reflectance, you see we have massive reflectance when we actually come in from the outside. So that's what we want. We reflect really the heat that the sun produces, while though in the inside, we keep the black body irradiation in the house. So this should be really a perfect system for broadband chirped mirrors. Clearly, we can go beyond buildings. We can use them in greenhouses. Finally, to end, clearly, now we took care of the visible. We took care of the infrared. The last thing we should not forget is the UV part. What we also can produce with the mirrors are materials that reflect the UV. So this is shown here, the same mirror they show for free, actually. The second order reflection we get directly in the UV. And we can actually manipulate where this second reflection comes. And this is a reflection, not absorption. So most of the UV protection layer usually absorb the UV, but therefore they also degrade over time. Here now we have a system where we can nicely manipulate the UV reflection. There's of course many options, maybe not on the building, otherwise we just reflect all the UV on people. That's maybe not a good thing. But where we really could have potential for such mirrors is in the extraterrestrial radiation. When you compare actually the UV on Earth and outside in space, you see actually there's a big difference. Here we are shielded, at least at the moment still, from the UV, but outside not. So wherever you need actually solar cells working outside, this could be an option. So with that, I think I should stop. I just go to the, I hope it works, summary. I hope I could show that manipulation of light is very, very promising. It would be great to have materials that do it also over large areas. And one is definitely the heat management sector. I think a lot of inorganics could work also for the PVs or lasers or LEDs, as long as they're transparent in the visible. In our case, we really use a superbly simple material, titanium tetrachloride, which is really the precursor to titanium dioxide, which we use all the time, just white walls, etc. Then polymer alcohol, used in many, many commodity plastic applications, possibly most importantly for oxygen scavenger in products. And with that, I should thank the people who really did the work. A lot was still done at Imperial College. The first row shows the students that started the work, together with physicists Donald Bradley and Paul Stavrinou, who really helped with the photonic device design. Adam Amassier at KAUST, and Walter Caseri, a chemist at ETH. And now, oops, I thought I have them clearly at Georgia Tech. We continue this with Alex Balzer, Connor Perry, and Marlo Durbin will more explore these options in the bioelectronics world. And I didn't get so far. We can use a lot of those systems, actually more complex type of mirrors, cavities, And together with Carlos Silva here at Chemistry and Physics, we think that's a pathway towards quantum materials where we can confine materials in these cavities for entanglement. I have actually no clue what that means, but we can definitely do the cavities. So with that, thank you. And in case there's still time for question, I'm happy to answer them. I think we're fine looking at the watch.
Question. Natalie, when you showed the cross-section of the organic PV with your refractive factor on top of it, you had a glass layer in the middle of your reflector. Why is that?
Often we use, and actually maybe I can show some of the, if this, let me see, I killed my mouse pad. We most of the time dip code, and hopefully, I don't know how to make animation, so let's wait till it syncs. So we dip code, so in case you have here a glass slide, so for free we get actually most of the time mirrors on both sides. So that's why. And we use that actually for anti-reflection coatings. So this has extremely nice optical effect that we can use and we get for free when we make actually here a very simple cavity on that side. So you see the white part in the middle is the glass slide. So you dip it in, you get the coatings on both sides. We can prevent that like what we did over here for this one, just by putting a cover layer on the other side that we then rip off. But most of the time, it actually helps us, especially also for heat mirror applications, etc., because it's easier to make 40 layers, because in principle, you only have to make 20.
And how do you control the thickness?
The thickness we can control with the viscosity, so that's why PVA is so nice. We can get all the molecular weights and the dipping speed. And it's remarkably reproducible, because we can reproduce the mirrors. I was actually skeptical, but the mirrors show that it's superbly reproducible. So we stick to the dip coater, and actually moving here, we bought a very big one. Unfortunately, Connor, he broke the leg, so the student who set it up is not here, but I'm very happy to have now this automated system. Because you can imagine a student making 40 layers. It takes a day or more. Alex maybe knows. So now we have to automate. Yeah.
If you dipping technology to apply multiple layers, the overall area would be uniformity.
The uniformity is very good. The only thing we have, but you will have that nearly with any coating technique, you have edge effects. So actually, therefore, the thicker you make it, the better, because the central is very homogeneous. You have, it can actually help us, especially with some of the cavities we want to have one side thicker, but we have not really seen, at least in the mirrors, drastic effects. So you have, like you said, at the bottom, a bit of a thicker layer, but again, that also depends on viscosity. Yes, it does, as I mentioned. So you see that, that's why the mirror shifts to lower wavelength. So when we make mirrors, we anneal, the stop band changes. In case it would not change the thickness, the intensity of the reflection only would get enhanced because you change the refractive index contrast, but it also shrinks. But in a very reproducible manner, we know exactly how much it shrinks, and therefore we can shift the stop band. So you can actually make a bit of a temperature sensor with it.